Hi guys, and welcome back to the second teaching video in Physics 1.4. Here we're going to look at some useful formulas and equations when talking about waves. So this video is going to cover important properties of waves, including amplitude and wavelength, frequency and period, velocity, distance and time, and how these all relate through equations and formula that you will need to know. So the first thing we're going to talk about is amplitude. The amplitude of a wave is all about how intense it is. So for sound, a bigger amplitude is going to mean a louder sound, and for light, a bigger amplitude is going to mean a brighter light. Here's a transverse and longitudinal wave explaining amplitude. So a wave's amplitude is the maximum distance that the medium moves from its middle position. So in our transverse wave, we have our series of peaks and troughs. The middle position is the line between these two, and the amplitude of the wave is the maximum distance that the medium moves from the middle position. So the furthest it gets from the middle position is here, or here. So this is the amplitude of this transverse wave. It's not from here to here. You only measure it from the middle position to the maximum distance that the medium moves. For a longitudinal wave, it's harder to measure. We think about amplitude as how close the compressions are. But if you're asked to draw a diagram explaining amplitude, we recommend that you do it using a transverse wave as it's easier to label. So on a transverse wave, an amplitude is half the distance between a crest and a trough. A bigger amplitude is going to mean a more intense wave and influences how it's experienced by us. The next thing we're going to talk about is wavelength. The reason that microwaves are actually called microwaves is because of their wavelength. Although electromagnetic waves generally have quite a small wavelength, on the scale of electromagnetic waves, microwaves have a very small wavelength, and this is why they're called microwaves. So again, here's a transverse wave and a longitudinal wave explaining wavelength. One wavelength is the distance from one point on the wave to the next equivalent point. And by equivalent, we mean similar. So on this transverse wave, we take one point in the wave, such as this crest, then we measure the distance to the next similar point, so the next crest. This is one wavelength. We can also measure it from one trough to one trough, or from the middle position before a crest to the next middle position before a crest. They're all going to be the same distance. So one wavelength is the distance from one point on the wave to the next similar point. In longitudinal waves, it's exactly the same. We can measure it from one compression to the next adjacent compression, and this is one wavelength, or we can measure it from the point between compressions to the next point between compressions, and this is also going to be one wavelength. When using equations, this is the symbol that we use to describe wavelength. Make sure that you're able to draw something that looks roughly like this, and also know that this symbol means wavelength, so that if you come across it in an exam, you know exactly what they're talking about. The next thing we're going to talk about is frequency and period. Frequency is the number of crests if you're talking about a transverse wave, or compressions if you're talking about a longitudinal wave, that pass a particular point every second. So here we have wind blowing water on a pool, and we have big ocean waves. If you were to stand in the pool and count how many of these little waves passed you in 1 second, you might get 1 or maybe 2. If you were to stand in the ocean and count how many waves broke over you in 1 second, you're probably going to get 0. You're only going to get one wave coming every 7 or 8 seconds. Frequency is the number of crests or compressions that pass a point every second. So these little waves on the pool have a much higher frequency than these big waves in the ocean. Frequency is measured in hertz, and the symbol that we use is a capital H and a little z. Period, which we abbreviate as a capital T, is the time that it takes for two crests next to each other to pass a point. So if you stood in the pool and you measure the time between one wave passing you and the next wave passing you, you might get, say, half a second or a second. If you stood in the ocean and measured the amount of time between one wave breaking over you and the next breaking over you, you're going to get around 8 or 9 seconds. The big ocean waves have a longer period than these smaller waves in the pool. Notice that the waves in the pool will have a higher frequency but a smaller period, and the waves in the ocean have a lower frequency but a longer period. This is because frequency and period have what we call an inverse relationship, so they move in opposite ways to each other. In maths, an inverse relationship is written as 1 divided by something, so we use this equation pretty often. F, which is frequency, equals 1 divided by t, which is period. This is that inverse relationship. If you were given period, or the tools to work out period, you can easily work out frequency by just going 1 divided by period. This also holds up the other way around. If you're given frequency or the tools to work out frequency, you can easily work out the period by going period equals 1 divided by frequency. So here's a practice question for frequency and period. You're in a boat bobbing on the waves. You count 18 waves in 1 minute. Calculate the period and frequency of the waves. Pause the video now and have a go. Then press play when you're ready to see the answer. So firstly, we're going to calculate period. And remember, the period is the time that it takes for two crests next to each other to pass through a particular point. So we can calculate this by dividing the total amount of time that we're counting for by the total number of waves. We counted for 1 minute, but we should always use seconds. So we counted for 60 seconds, and we should divide this by the 18 waves that we counted. This means that the period that we get is 6 seconds. So one wave is passing the boat every 6 seconds. Next, we need to calculate the frequency of the wave. And remember, frequency and period have an inverse relationship. So frequency is equal to 1 divided by period. If we plug in the answer that we've just got, frequency is equal to 1 divided by 6. And this is equal to 0.167. And the unit that we use for frequency is hertz. Next, we're going to talk about velocity. Remember, for a specific medium, for example water, the speed or the velocity of a particular wave is constant. Velocity or speed is equal to the distance that a wave travels divided by the time that it takes to travel that distance. So we use this equation v equals d divided by t quite a lot. When we're talking about velocity, we always have to put our distances into meters and our times into seconds. Otherwise our answer is going to come out wrong. Velocity is measured in units of meters per second. Here's a practice question for velocity. A wave is generated in the center of a bucket of water from a dripping tap. The wave's speed is 0.5 meters per second, and it takes 0.4 seconds to travel from the center to the edge of the bucket. Calculate the radius of the bucket. Pause the video now and have a go, then press play when you're ready to see the answer. So we've got to use this equation v equals d over t, but we're given velocity and we're given the time, and we want to calculate the distance, the d. So we have to rearrange this equation by putting the t on the left-hand side. To do this, we multiply it by the velocity. So distance equals time times velocity. Then we plug in our numbers. The time that the wave takes to travel is 0.4 seconds, and the velocity that it travels with is 0.5 meters per second. So the distance that it's going to travel in that 0.4 seconds is going to be 0.4 times 0.5, and that comes out as 0.2. Remember, this is in meters, so 0.2 meters is the same as 20 centimeters. So how do all of these concepts relate to each other? This is an important equation that we want you to memorize. The v stands for velocity, the f stands for frequency, and that funny symbol that we call lambda stands for wavelength. Scientists have found that the velocity of a wave is equal to the frequency of that wave times the wavelength of that wave. This is an important equation that we recommend you memorize. So here we have a transverse wave, for example light, and it's traveling through one specific medium such as air. From this wave to this wave, the wavelength has decreased, and we can see this on the diagram by this distance here becoming shorter in the second wave. We know that if the same wave travels through the same medium, the velocity is constant. So this is not going to change. And if we know the wavelength has decreased or gotten smaller, and we know that the velocity stays constant, then we know that frequency is going to move in the opposite way to the wavelength. Otherwise, if it didn't, the velocity would change. If the wavelength is decreasing, then the frequency is going to increase to maintain a constant velocity. And if we look on the diagram, we can see that the frequency is increased. Here we can count 2 troughs over this particular distance, whereas in this wave, we can count 5 troughs, so the frequency has increased. You should be able to know this equation off by heart, including what all these symbols mean, and use it to be able to calculate one of these variables. So here's a practice question. The frequency of a sound wave at a particular note is 256 Hz. The speed of sound through air is 330 meters per second. Calculate the wavelength of this sound wave. Pause the video now and have a go, and press play when you're ready to see the answer. So this is our all-important equation. Velocity equals frequency times wavelength. We want to calculate the wavelength, so we have to rearrange this equation into wavelength equals velocity divided by frequency. So all we've done is put the frequency on the left-hand side and divided our velocity by this frequency. So wavelength equals velocity divided by frequency. We're given the velocity is 330 meters per second, and we're given the frequency is 256 Hz. So all we have to do is plug in these numbers, and we get a wavelength of 1.29 meters. So here's what you need to know for this video. We talked about amplitude and wavelength, where our amplitude is the distance from the middle position to the maximum distance that the medium moves. And in a longitudinal wave, it's harder to measure, but we talk about it with regards to the closeness of the compressions. The wavelength of a wave is the distance between one point and the next similar point. So the distance between two crests, two troughs, the distance between two compressions, or the midpoint between compressions. Each of these is one wavelength. Then we talked about frequency and period. These are about the timing of waves. So the frequency is how many waves pass by a point per second, and the period is how long it takes between two waves passing a particular point. And these have an inverse relationship, so period equals 1 divided by frequency. Then we looked at velocity, distance, and time, and how velocity is equal to the distance the wave travels divided by the time that it takes to travel that distance. Then we learned this equation, velocity equals frequency times wavelength, and used it on a practice question.